All right, hello everyone. Let's continue our topic on the fundamentals of environmental engineering and sciences. So this class we're going to talk about the water quality in rivers. And before we do that, let's do a quick recap again about our last class. So last class we talked about the water pollutants and their sources, right? So we differentiated the point sources and non-point sources, and we talk about the all different types of water pollutants. For example, nutrients, pathogenic organisms, suspended particles, suspended solids, salts, pesticides, arsenic, heat, and nanoparticles, right? So this class we're going to talk about how we can evaluate the water quality. So this, as I said, this class we're going to talk about the water quality management in rivers, okay? So we know that in the water there are a lot of oxygen demanding materials. And because of these oxygen demanding materials, for example, the leaves or the ooze that's in the water or some chemicals, organic chemicals. So because of these oxygen demanding materials, they will go through oxidation when they're existing in the water. And because water can dissolve oxygen, so they can react with the oxygen and then get oxidized. And this will lead to a reduced dissolved oxygen in water. And if the oxygen amount in the water is reduced, it's going to be a threat to the fish and other higher forms of aquatic lives. For example, if we saw a lake or some water looks like this, we can directly guess that there are not many lives in the water, right? It is not because of the smell or the color of the water. It is actually because of the lack of oxygen, because there are a lot of oxygen demanding materials in the water, right? So then we know the definition of the oxygen demand. Okay, so if the oxygen demand is larger than the dissolved oxygen, it means that it demands more oxygen that can be dissolved in the water. Okay, so this will simply leads to that there's no fish in the water, right? Simply speaking, or other levels of lives in the water. And if the oxygen demand is smaller than the dissolved oxygen in the water, and maybe there will be fish, because the water might still the water might still be polluted because of all of these oxygen demanding materials. So because of that, there are different forms of the oxygen demand. Okay, so the first one we're going to learn about is called the theoretical oxygen demand. So it is defined as the amount of oxygen required to oxidize all of these oxygen demanding materials to carbon dioxide based on the stoichiometry. So a simple example can be that how can we calculate the theoretical oxygen demand of the glucose or of wastewater that's containing glucose. So we know that the glucose, if we write out the chemical formula, is C6H12C6O6, right? And then we can easily calculate what is the required oxygen to oxidize all of these to carbon dioxide and water. So if we write out the chemical formula or the chemical reactions for the oxidation of the glucose, you know that it's going to need oxygen. So first, you can see that the water is already in stoichiometry, so that's going to give us 6 water, and then we're going to oxidize all of this carbon to carbon dioxide, which is 6 CO2, right? So because of that, we need 6 oxygen in this equation, all right? So how do we calculate the theoretical oxygen demand? So because we already know the concentration of the glucose in the wastewater, so we can use that to first calculate what is the molarity of the glucose. So that is 108.75 divided by the molecular weight of the glucose. And that turns out to be 180 gram per mole. Okay, we'll divide that by 180. All right. So we should still notice that the units here are milligram per liter, and here is gram per mole. Okay. All right. To guarantee that the units are conserved, we need to multiply this by 1,000 to yield milligram per mole, right? And further, we can convert this to the amount of oxygen that's needed, because we're going to need six times of the molarity of the glucose, right? And then we also need to multiply the molecular weight of the oxygen, which is 32. And if we want to convert it into milligrams, we need to multiply by 10 to the third milligram per mole. Okay, so these things 10 to the third can get cancelled out, and you can find out that the solution for this equation is 116 milligram per liter of oxygen. Okay, so based on the stoichiometry of the reaction, and also the concentration of these oxygen demanding material, we can directly calculate what is the theoretic oxygen demand. But we have to mention that this is almost impossible in the nature, because I think that we directly sample some water from the river or the lake nearby. We don't really know what is the detailed chemical composition of the water, because there can be all types of organic materials inside, right? And each of them are going to have a different type of this stoichiometry, and that's going to lead to a very complex calculation, or it's almost impossible to calculate this theoretical oxygen demand. So because of that, we have to determine this oxygen demand through some experiments. So people have thought about doing experiments directly by oxidizing all of these organic materials. So that's why we invented a term called the chemical oxygen demand, or the COD. So what COD means is that it is the amount of oxygen required to oxidize all of these oxygen-demanding materials to carbon dioxide based on experiments using a strong oxidizing agent, for example, the chromic acid. All right? So we're using a very strong oxidizing material to basically oxidize all of these organic materials in the water. Okay? But we have to mention that this might be an overestimate of the oxygen demand for the water. For example, if we go back to this picture here, you can see that there are a lot of plastic bags inside, right? So the plastic bags are very stable in the water. They're not getting easily oxidized, or they're not demanding the oxygen really quickly. They can stay and change the water for even millions of years, right? So this means that the oxygen demand that we determine from this complete chemical reaction is going to overestimate the oxygen demand in the water, simply because some of the organic matter is not biodegradable, so it's less likely to harm the environment or directly harm different levels of the lives. And simply because of that, we have to think of a more realistic way to quantify the oxygen demand. And this more realistic parameter is called the biochemical oxygen demand, or the BOD. So the BOD determines the oxygen consumption by the microorganisms when the organic matters are being degraded. Okay, so this is a more realistic way representing the oxygen demand, because there's always some microorganisms in the river water or in the lake, right? And of course, there may be some, for example, if water emitted from the industrial plant is too polluted, there might be no microorganisms at all, but we can still dilute them and then add in some seed, which are basically these microorganisms, to try to calculate what is the oxygen demand for these polluted water. Okay. So people like this definition, or like this parameter, because it also reflects the biodegradability. So it is more, it can be more related to the environment. Okay. So also it uses the bioassay. So basically, these bioassays use the microorganisms in conditions that are similar to the natural water, because we don't want to add some super bacteria that can quickly consume all of these organics. We still want to get a realistic understanding of how fast these oxygen-demanding materials are being oxidized. Okay? So since we know all of these conditions, all of these parameters, for example, the theoretical oxygen demand, COD and BOD, so what are their relationships? So for these three oxygen demand, we know that under very rare circumstances, the theoretical oxygen demand is going to be equal to COD. This is only when the wastewater is containing very simple organic matters. For example, if it just contains the simple sugar, for example, the glucose, or glucose adding some other types of very well-known sugar types. Okay, so under these conditions, the theoretical oxygen demand is going to be equal to the COD. But for most of the circumstances, most of the conditions, they are not equal. And also, we should know that the BOD never equals to the theoretical oxygen demand or the COD. And this is simply because some of the carbon or some of the organics in the water are being converted to part of the microorganisms because they survive on these organic matter, right? So they will not get oxidized into carbon dioxide. And also some carbons were converted to soluble organic matter. And these are basically the waste that's being generated by these microorganisms, because after they digest all of these organic matter, they're going to emit some waste, and these wastes are also most of the times are organics, and they're not converting them into carbon dioxide. So that's why the BOD never equals to the theoretical oxygen demand and or the COD. But BOD is most used as it represents the natural processes. So basically in this class, we're going to use the BOD as an indicator of the water quality in all different types of the water systems. So how do we measure the BOD? So let's just imagine a very simple scenario, okay? So we find a bottle, okay? We just use a bottle to collect some river water or lake water and then bring it to the lab. So the water might already contain some of the microorganisms inside. So since the water also has dissolved oxygen, so these organisms can already start to oxidize all of these oxygen-demanding materials, right? Or if the water quality is so bad, it doesn't have any microorganisms, we can add in these seed materials into the water and then let these microorganisms to do the job, right, to oxidize these organics inside. So how will the organic concentration change as a function of time? So we have learned from the different types of reactor, right? So basically this bottle is a batch reactor. Okay, you have all of these nutrients or all of these organic matter in the bottle, right? And then we have reaction taking place in the bottle. And this is a batch reactor because it doesn't have an inlet or it's not a continuous process, right? And for a batch reactor, the reaction kinetics can be determined by this equation here. And so this is basically assuming that the reaction or the consumption of the organic matter is a first order reaction. So the concentration of the organics in the water, which is L, so dL divided by dt is going to be equal to negative KL. Okay, so this is assuming that the reaction is a first order reaction. And the L is concentration of the organic chemicals. And if we integrate this differential equation, we can get the concentration of the organic materials as a function of time. And we know that for these this type of differential equation is going to give us a exponential decrease of the concentration, right? So if we plot out how the concentration change as a function of time, you can see that it's going to decrease exponentially. And this is simply because at the beginning, there is a lot of these organic materials. And this means that they're going to be consumed at a faster rate but as their concentration decrease and decrease, the concentration or the reaction rate will decrease. This represents what's taking place in a first order reaction. Okay, this is going to be T, L, and then it starts from L0. Okay, so this is the concentration of the organic materials. So how do we convert that into BOD? Okay, so for the BOD, it's going to be the reverse of this concentration, because we know that the oxygen demand, for example, let's say this is another representation of this concentration plot here. So if we notice, basically this line here is the concentration of the organic materials as a function of time, right? And the BOD, or the oxygen demand, is going to keep increasing as a function of time, right? For example, at 30 minutes, although the concentration of the organic matter decreased, but the BOD at 30 minutes is, which is a cumulative oxygen that's demanded by this water, is almost to the highest value, right? So the BOD under this situation is just calculated by the initial concentration of the organic matter minus the organic matter concentration at any time. And that's calculated by this equation here, okay? Which is L0 multiplied by 1 minus exponential minus KT, all right? And we can also know that for this experiment, there's going to be a highest value of the BOD, or the maximum amount of the oxygen demand, which is L0. So the L0 is also called as the ultimate BOD, which is the highest biological or biochemical oxygen demand. All right. So, for example, let's say if we know that there's a 3-day BOD, or called BOD3, typically just add this subscript following the BOD to represent how many days, or what is the time that has lapsed. Okay, so if the BOD3 of a waste is 75 milligram per liter, and the BOD decay constant, which is a K here, is 0.345 per day. So what is the ultimate BOD? Okay, so we can directly use this equation here. We know that the BOD3 is going to be equal to L0, 1 minus exponential minus KT. So in this scenario, K is equal to minus 0.345, and T is equal to 3. Okay, so we can further find out that basically here is actually equal to 0.645 L0, and then since BOD3 is 75 milligram per liter, we can calculate what is the ultimate BOD. 75 divided by 0.645, 116 milligram per liter, right? Okay, so basically this equation tell us what is the BOD at any time, but it doesn't tell us how fast the oxygen is being consumed. So actually, if we talk about how fast the reaction is, it's always involved in the reaction kinetics. And we know that reaction kinetics is closely related with this rate constant here, okay? So basically, this rate constant depends on the following conditions that determines how fast this reaction is. So first, it's dependent on the nature of the wastewater. For example, if the wastewater is composed of simple sugars, then that's very easy for these microorganisms to degrade these organic materials. Okay, but if it's composed of very complex or very difficult to degrade organic materials, then it's going to take a long time for the reaction to take place. And it also depends on the ability of the microorganisms to use these waste. For example, it depends on the type of the organism, because we know that specific type of bacteria they can target, or they can easily degrade very complicated organic materials. But most of the bacteria or these organisms are not that easy to degrade that. It also depends on what is the amount of these microorganisms in the water. And of course, it depends on the temperature. So at the beginning of the class, when we review all of those chemical concepts, we know that the reaction rate is dependent on the temperature. Okay, so we mentioned that the higher the temperature, the higher the reaction rate. And actually, it was because the higher the rate constant. So if you recall that relationship there, we can again write out this equation. So the reaction rate at any time at any temperature is equal to the reaction rate at a reference temperature multiplied by a constant with an exponential of the temperature here. Okay, because of this relationship, we can always derive this this trend here, which is the higher the temperature, the higher the rate constant. And you can find out that the theta here, which is a constant that's being used in this equation, and for typical domestic wastewater, it has a value of 1.135 in the temperature range here, and 1.056 in the temperature range here. Okay, so basically at any temperature we can calculate what is the rate constant for this biological process. Okay, so we can go through another example here. Let's say that a waste is being discharged into a river that has a temperature of 10 Celsius. It also asks us what is the fraction of the maximum oxygen consumption that has occurred in 4 days, which is basically the BOD4. And if the rate constant is determined in the lab under the standard condition, which is 0.115 per day. Okay, so first we need to calculate what is the rate constant under the real condition, or under the actual condition, which is 10 Celsius. So we can use this relationship here. Basically, KT is equal to K20 multiplied by theta to the power of T minus 20. All right, so we know that K20 is 0.115 multiplied by theta. We notice that between, so this is the temperature at 10 Celsius, and we know that for the theta between 4 and 20 Celsius is 1.135, right, to the power of 10 minus 20, right? So by plugging in these parameters, we can find out that actually this new KT is equal to what? It's equal to 0.0032 per day. All right, and because of that, we can calculate what is the BOD4. So the BOD4 is equal to L0, 1 minus exponential minus 0.032 multiplied by 4, right? So, and also it asks us what is the fraction. So basically we were calculating BOD4 divided by L0, which is this equation here. We can find out that this is 0.12. Okay, so let's think of another situation. Let's say that now we are measuring this, we're measuring the water quality at 20 Celsius. Okay, we're still calculating what is the BOD under 4 days. Is it going to be larger compared to this value or smaller compared to this value? Actually, it's going to be larger than this value, right? Because under 20 Celsius, a K is going to be a larger value. So you can find out that in this equation, okay, so if the K increases, basically if the temperature increases, K will increase. So this term is going to decrease, right? And this whole term is going to increase. Okay, so which means that the BOD4 divided by L0 is going to increase. right? So you can clearly see this temperature dependence of the BOD, okay? So here we basically introduce a concept how we can measure the BOD, but how we can theoretically or more accurately determine the BOD. And actually, you're going to start to do a lab session this Wednesday and Thursday about the laboratory measurement of the BOD. So the measurement of the BOD typically needs 4 steps, okay? So for these measurements, we're going to use standard bottles that are exactly 300 milliliter to contain the wastewater, and then we're also going to do these controlled measurements. For example, we need to set up the experimental group, right? And then set up a control group to compare the results. So here is a brief steps or brief procedures of how we can measure the BOD in laboratory. So the first step is to find a or to use this 300 milliliter bottle. It's not BOD, bottle. 300 milliliter bottle that's completely filled with a sample water. The sample water has to be appropriately diluted and also inoculated with microorganisms. So there are 2 sections, okay? So for this bottle here, let's say this is our bottle, right? It has to be exactly 300 milliliter because they have to be standard, have a standard volume there. So first, it has to be properly diluted. So you may wonder, why can't we just use the wastewater and then put in a sample there without any dilution? It is actually because if the BOD of this sample is too high, let's say is at maximum, okay, so, and we have introduced that if the oxygen demand is larger than the dissolved oxygen, if the oxygen demand is larger than the dissolved oxygen, it simply means that all of the or none of the microorganisms are able to grow in this sample here, okay? So let's say if the BOD is too high for this sample, we cannot directly put this sample into the bottle and measure the BOD because no organisms are going to live or are going to oxidize these oxygen demanding materials. So we have to dilute it properly, okay? So actually for this dilution, the BOD has to be between the range of 2 to 6 milligram per liter. And this is mainly because the dissolved oxygen or the maximum dissolved oxygen in the water is around 9 milliliter, 9 milligram per liter, okay? So we have to make sure that the BOD in this bottle is lower than this value, and it's recommended that the BOD after dilution should be between 2 and 6 milligram per liter. And also, it has to be inoculated with the microorganisms. So this is quite easy to think about, right? Because we need to have to make sure that there are enough organisms in the bottle to conduct this oxidation process. Okay, and because of this dilution process, we can define some parameters. Okay, so we define a term called the sample size or the dilution factor. So basically, the sample size is a parameter that's shown in fractions. Let's say if the sample size is 10%, it simply means the dilution factor is 0.1. Okay, so the sample size or the dilution factor is defined as the volume of the undiluted sample divided by the volume of the diluted sample. Okay, so if it's sample size, then you need to multiply this number by 100. If it's dilution factor, you don't have to consider that. Okay, so for example, if we put 30 milliliter of the wastewater into this 300 milliliter bottle, and then the rest of it is composed of the diluted, or is composed of the pure water. Okay, so what that means simply is that volume of the undiluted sample is 30, volume of the diluted sample is 300, and that's going to give us a 10% of the sample size, or 0.1 of the dilution factor. Okay, so here's an example on how we can determine what is the sample amount we should put into this BOD bottle. So let's say the BOD of a wastewater sample is estimated to be 180 milligram per liter. So we know that this number is much, much larger than 9 milligram per liter, right? So because of that, we have to dilute this sample here. Otherwise, no organism can live in this sample here. So it asks us what volume of this undiluted sample should be added into this 300 milliliter bottle, and also what are the sample size and dilution factor of this using this volume. So it assumed that the final BOD should be around 4 milligram per liter. Okay, so so basically, to solve this problem, we need to first calculate what is the sample size. Okay, so we can find out that the sample size, as the definition, is actually directly equal to 4 milligram per liter divided by 180 milligram per liter. Okay, so this is going to be the approximate sample size. Okay, and then to calculate what is the amount of the sample that's putting into this 300 milliliter bottle, we'll multiply this by 300 milliliter. And you can find out that this volume is actually 6.66 milliliter. Okay, so during our experiments, it is very difficult for us to control this volume or this sample volume to be 6.66, right? It's we have to be very accurate to do that, and also it's very difficult for us to find the correct volume to basically extract the same amount, this exact amount. So what we do is that we're going to round this volume to 7 milliliter. Okay, so we're going to put 7 milliliter of the sample into this 300 milliliter bottle. And what that simply means is that the sample size is going to be 7 divided by 300, okay, and multiply by 100%, which is 2.33%. Okay, so the dilution factor is going to be equal to 7 divided by 300, which is 0.0233. Okay, so this is typically how we can decide what is the sample size, or what is the sample volume we should put into this BOD bottle. Okay, so the first step is the proper dilution, also the inoculation of the microorganisms. So the second step is to set up a blank sample. So basically, the first bottle we have is the wastewater, and also with the microorganisms, right? So for example, we also have to properly seal this bottle here, right? I'd say there are some microorganisms. Let's use green to represent that, okay? And also there are some, so let's say the green dots are the organic materials or the oxygen demanding materials, and the black dots are these microorganisms, right? So what we would also do is to find another BOD bottle, which is a blank sample. Okay, so this BOD bottle is going to be exactly the same in terms of volume, but we don't have any sample in there. So what this contains is just a diluted liquid, or diluted liquid that's being used in this bottle. So it's also going to contain the bottle there, but it's not going to have any of these organic materials or these oxygen demanding materials, but we're going to have these microorganisms. So the reason why we set up this control group is mainly considering maybe the diluted liquid or the dilution liquid also contains some of the organic materials, and then that's going to give us a BOD from this dilution process, right? So by comparing the oxygen, dissolved oxygen for this experimental group and the control group, basically by subtracting the the dissolved oxygen from these two groups, we can calculate what is the BOD that's purely contributed by the oxygen demanding material that's in the wastewater. Okay, so basically the second step is to set up the blank samples that's containing only the inoculated dilution water, and also are placed into these BOD bottles, right? And the blanks are required because we need that to estimate the amount of oxygen consumed by the added inoculum in absence of the sample. Okay, so the third step is to incubate both of these samples, both of these bottles in the dark for 20 Celsius, because 20 Celsius is the standard condition for determining the BOD for these desired number of days. Okay, for most of the purpose, 5 days is used. You can also find that we use the BOD 5 quite a lot for a lot of the water quality examination. Okay, so the reason why people use 5 days is actually it also have some historical background, and this is mainly because the water, as I have introduced in the first class in the introduction, so the water treatment or the wastewater treatment originated from England, right? In England, most of the water are coming from, or drinkable water, are coming from the Thames River. Actually, the 5 days is the length or is time that's needed for the Thames River to originate or to pass the city and then finally get emitted to the sea. Okay, so from the origin to the sea. Okay, so this that's why people have kind of inherited this history here and then use a standard 5 days to represent water quality. So people use this BOD 5 quite a lot. So for your experiment, because if you do the experiments on Wednesday or Thursday, then it's not going to be exactly 5 days for next experiment, right? And also for the students that's taking the class on Monday, or if their lab is on Monday or Tuesday, then they have to come over the weekend. It's quite inconvenient for them. So that's why we typically use 7 days or 10 days for our experiments, right? So the final step is to collect all of these data. So after these desired days are elapsed, so we're going to first measure the dissolved oxygen, and then we can calculate the BOD based on the dissolved oxygen for this experimental group and the control group. Okay, so we can use a simple way to calculate the BOD. That is directly the oxygen, the dissolved oxygen in the blank group minus the dissolved oxygen in the sample group. Okay, so if we think back on these two bottles, okay, so after 5 days, for example, which one is going to have more dissolved oxygen? It's going to be this bottle, right? Because this bottle almost doesn't contain the organic materials. Okay, and because of that, it's going to consume less oxygen, and that's going to give us more dissolved oxygen in the control bottle. All right, so that's why we put the control bottle, the dissolved oxygen first, minus the dissolved oxygen in the sample bottle, and this is going to give us what is the dissolved oxygen that's consumed by these microorganisms in this sample bottle. And of course, we have to divide the whole thing by the dilution factor, because it's after proper dilution, right? And then this is mainly because the dissolved oxygen that's being consumed by these organisms is just a fraction of the entire wastewater. So that's why we also need to divide this P here to consider the dilution process. And for a more accurate determination of the BOD, we can use this equation. The reason why we have to use this more complex equation is that we can only use this equation if the BOD in the seed water or the dilution water is negligible. Okay, let's say we're using ultra pure water that doesn't have any doesn't have any organic materials or oxygen demanding materials, then we can use this equation. But for most of the time, the seed water or the dilution water might contain some of these organic materials. And that's why we have to use a more complex equation. So basically, here, so the first term represents the dissolved oxygen in the sample bottle. Okay, so the dissolved oxygen amount at the initial time minus the dissolved oxygen at the final time, or after certain days elapsed, minus the blank dissolved oxygen at the initial time minus the dissolved oxygen of the blank group at time t multiplied by this F here, okay? And this whole thing is going to get divided by the P, which is the dilution factor. That is going to yield the BOD at any time. So this F is further defined as the ratio of the seed in the diluted sample to the seed in the seed control. So basically, it's the volume of the seed in the diluted sample. Basically, it's the volume of so the seed is the basically the volume that's containing the microorganisms, right? Normally, the seed is going to have a small volume because it's very concentrated with all of these microorganisms, okay? And we're also adding seed into this blank group here, okay? So the F can be calculated by the volume of the seed in the diluted sample divided by the volume of the seed in the seed control, okay? So this equation looks quite complex, but we can use a simple example to show how we can calculate this BOD at any time, okay? So let's say that we have two bottles. We have the sample bottle, which is the experimental group, and we have the blank or the control group here, okay? So for the sample group, it is a 300 milliliter bottle. It has 3 milliliter of the sample, 1 milliliter of the seed, and at the initial time, the dissolved oxygen is 8. At the final time, the dissolved oxygen is 3, okay? It's 3 milligram per liter. And for the blank control, we're adding more seed. You see that here is 1 milliliter of seed, but here we actually added 2 milliliter of the seed. So at the initial time, for the blank group, it's 8.5 in terms of the dissolved oxygen, and at final time, the dissolved oxygen is 7.5. Okay, so how we can calculate the BOD if the results looks like this? Okay, so we can directly list the equation. So BODT is equal to, so first in the bracket is the sample condition. Okay, so it's DOSI minus DOST minus DOBI minus DOBT multiplied by F divided by P. Okay, so let's plug in these numbers. All right, we have initial is 8 minus 3 minus what? 8.5 minus 7.5. What is the F? So the F is calculated by the volume of the seed in the diluted sample divided by the volume of seed in the seed control. Volume of the seed in the diluted sample is 1, and volume of seed in the control is 2. So the F is equal to 1 over 2, right? And what is the P here? So the P is the dilution ratio, right? So the dilution ratio is defined as the volume of the sample, or the undiluted sample, divided by the volume of the diluted sample, right? So that's going to be divided by 3, divided by 300. So basically, this whole thing have to multiply by 100, okay? So we can remove this term here, right? So with this equation, we can start to do the calculation. You can see that the final BOD, or the calculated BOD, is 450 milligram per liter. So this is how we can use this more complex equation to determine this BOD. So for your experiments on calculating the BOD, the mechanism might be a little bit different, but it's following this similar idea here. And I'm sure you're going to collect, or you're going to learn more information regarding how we can determine the BOD from the wastewater. All right, so that's all for this class. And